Circuit. We use the CMPT101B sensor to obtain an isolated and reduced AC voltage signal, which the Arduino samples through an analog input and transmits the data to a computer via serial communication. We use 4 LEDs that are connected to our Arduino to provide visual feedback, which give us normal operation, warning, critical alarm, or no network connection. And wiring layout. We use pin connections in sensor signal, power, ground, and LEDs that were clearly separated, which simplifies testing, debugging, and integration into the mechanical case. Mechanical enclosure. We did the case to protect the circuit. The case had the constraints of the challenge, which were 100 millimeters of height and 150 millimeters of width. Engineered to protect the electronics and organize the internal wiring. The structure and validation. We successfully passed fusion stress analysis with our material, which was wood, and also a physical external load test.
Dale si quieres.
¿Ya?
Sí. Ya quedó.
Components were also soldered so that when we move the box, anything won't get disconnected. Circuit. We use the CMPT101B sensor to obtain an isolated and reduced AC voltage.
After testing the circuit separately, we place it inside the case. We organize the wiring to keep the internal space clean and to prevent loose cables from interfering with the components. We also checked that the Arduino, the sensor, the LEDs, and the cable outputs were correctly positioned. Some connections were soldered to make the system more reliable and avoid accidental disconnections during the demonstration. This part was important because the project had to work electrically, but also had to be present as a complete mechatronic system with proper physical integration.
So now for the code, we know that Python will be reading the data from the serial port, and we have to process it and send the information back to the Arduino to display the LEDs and our graphical interface. We have to investigate the following actions that we identified as fundamental to the project, but we didn't really know how to do them. And these are the codes from those actions, and we created our first draft. After that, we need to do a graphical interface that for this part, we did use artificial intelligence basically to give order to our code and make the graphical interface more clear. We can see here our first draft, and we can see here the final draft that we are presenting here. At the top, we see the sensor signal in the time domain, then the FFT transform it into the frequency domain, where the main peak appears near 60 Hertz. And at the bottom, we evaluate the triplet harmonics and compare them with the defined Armax that we can modify with a slider. Now for the demonstration of how this project works, now that you see that we have the AC voltage connected, we run the Arduino, and after we run it, we will run our Python code. And as you can see, now we have our graphical interface where we have the sensor signal in time domain. After we use FFT and the triplet harmonics, and also the Armax we can modify. And as you can see, the LED is turned on the green, and we will modify it. And as you can see, with 1.5 of Armax, the LED yellow is turned on. And as we reduce it, now with 1, we have the red LED turned on. And as we can see here, we have more information and the current status. If we unplugged our current, as you can see, now it will turn on the no network connection LED. And this is it.